deterministic and being represented by the sequence of on or off pulse. Okay, they also can be expressed in 0 or 1, which is bivalence, and also could be a binary signal. Okay, this diagram is a digital signal. That means respond to the timer. Signal is either 0 or 1. Okay, they don't have other than that. So this is a very basic digital signal. The next will be the analog signal or analog system. Analog system are the one where all the signal are continuous functions of time, and the size of a signal which is a measure of the variable. That means as you can see, there is a very big difference. They don't have the definitely 0 or 1. They will be come up with a lot of the decimal, maybe 0 point something, 0 0.1.2, 0 0.1.3, and then they will respond to the time. Okay, it's a continuous curve. It's not like they will stop in some way, either on or off. If they're on, they will keep on. Okay, when they stop, they straight away. They don't have the intermediate. They only have 1 or 0. Whereas for analog, there will be the continuous. That could be a 0.1, 0.15, 0.17. All number is possible for analog system. So if we look at the signal, okay, digital will be look like this form. Analog could be a sine wave form like this. Okay. So for the best, digital, we are using the discrete level, and therefore can only turn on any friction value or frictional value. For example, like 0 watt for low, 4 watt for high, or 5 watt or 0 watt. Okay. Whereas for the analog signal, it's a continuous wave denoted by a sine wave and may vary in signal strength, amplitude, or frequency. There are many examples of analog around us. That could be the human voice is analog, okay? Because sound waves are continuous, as is our own visions, okay? Because we see various shape and the color in a continuous manner due to the light wave, okay? If you only can see black or white, then your eyes is a digital, okay? If you can see other than the black or white, maybe yellow or green, then it will be an analog form, okay? May I ask you a question? A feeling, a man feeling, for example, if a man crash with a woman, do you think that is an analog or digital? Guys, please answer me.
Analog. Again, a man feeling.
A man fall in love.
A man
fall in love.
Fall
with
in love.
a woman.
Okay.
Or woman, is it analog or digital?
Analog. I think analog.
Analog.
Digital.
Analog, digital.
Digital.
Analog, digital.
Digital, sir, because the guy will
Money
kena reject or kena accept, sir.
Yes, very good. Only have two answer, ma. Yes or no?
Yeah, reject or accept, sir.
Yes, that's why it's digital. If a man love a woman very much, then it's a digital or analog. Guys?
I understand, sir, I understand.
If a man love a woman very much, is it analog or digital?
Analog.
If you say analog, please
Also,
give me your answer. Why analog?
because in a relationship there's ups and downs.
Sometimes
Yes,
feeling.
it's
sometimes
very-
not feeling.
Yes, it's correct. Okay, that's why. Because if your answer is not definitely yes or no, is a variance there, or the variance is continuous, that would be the analog. Okay, just like the sine waveform. Okay, sometimes you maybe if when your girlfriend is birthday, okay, then you treat your girlfriend very well, buy her a very good purse or whatever. Okay, then she will love you very much. Okay, so there will be a very high amplitude. Okay, so this is just a joke lah. So I will give you some typical digital signal used for in the automation. For example, like the input signal, as I keep on saying, switch position. Okay, switch position is a latch button. Okay, that means they will continuously latch the signal. This is analog. They only can turn on or turn off. Okay. How about the push button? Push button also momentary signal. They only give you one time signal, and this is also a digital signal. Okay. So this is an example of a digital signal. For output signal, the lamp, okay, either you turn on or turn off, motor on or off, solenoid valve open or close. Okay, so this is all is a digital, yes or no. But if you look into it, okay, for example, like oven, the temperature definitely is a analog because the temperature is keep on increasing or keep on reducing, or they don't have the finite answer. Okay, or fluid pressure and also the flow rate. So for output signal, that could be the control valve positions. For example, like you want to extend for 5 meter, or maybe next time 5.5 meter, that will be the vary the position. Okay, now the motor, the good thing is the motor. Just now I say motor is a digital signal, on off. That means I will turn on and turn off. Actually is for motor digital. Okay, when I talk about the motor speed or velocity, okay, that means this will be digital or analog. Why? Because the speed we can vary. For example, like we want to have a revolution per minute, maybe 5. After that, you want to increase to 6 or 7 or whatever figure is possible, as long as your VFD can provide this. Okay. And another one is the motor positions. Okay, this is especially for the stepper motor, where we want to rotate the angular positions. Okay, for example, we want to rotate to 5 degrees Celsius, 10 or 20 degree, depend on from your reference datum. Is possible. Okay, they can rotate, just like when we want to move our robot to twist, to turn 360 degree, all is possible. Then because this one will give you a continuous positions, that's why this is analog. Okay, so do you guys understand this one? Okay, now I want a representative from DMG and DMR. You need to select one to answer, to give me the example. One analog signal input and one output. Okay, and also digital. So I give you 3 seconds, not 3 seconds, 3 minutes. You think about it. Okay, element of you give me the example, and then when you say, for example, this is an analog signal, you give me name the sensor and tell me why. Okay, I give you 3 minutes, guys, please. Any volunteer from DMG? Hello? Do I talking with the A?
Sir, can you maybe repeat the last sentence where you say connect it to sensor? What do you mean?
Input signal. Not to say connect to sensor. Input signal. You give me the input signal.
Oh, okay.
I want the input signal because the input signal is a sensor. When you connect to the sensor is connect, is the input. Okay, you give me the input signal.
Input signal,
For
maybe
digital,
like a mouse click
mouse click, analog digital.
and digital.
Mouse click, analog digital, because it's a button. Okay,
Yes.
This is an input signal. How about the digital output signal?
Digital output. Maybe like the status of my fan is on or off.
Yes. Okay, to turn on the motor. Okay, because fan is controlled by the motor. Okay, because you say fan, then I accept lah. Okay, then how about the analog?
Radio signals.
Radio signals. What you mean by radio signal? The wave.
Yeah, radio wave lah, in your car radio
Yes.
or somewhere.
Okay, radio wave signal. Okay, it's an analog. Okay, can output signal? What is your output signal?
The sound emitted from the radio.
Sound emitted from the radio. Yes, because the sound when we speak, we have a different different tune. They will up and down. Okay, as you can see here, actually, I mentioned a human voice is analog because they are various. Okay, so you from where? DMG or DMR?
DMG, both of us are DMG.
Okay, good. Now it's DMR turn. Okay, DMR.
Sir,
Yes.
about the radio just now, can we say that the frequency for the output?
Output frequency. I don't want this. I want the output. I want output because frequency you could be input or out. You could be input or output. I want the very definite one. Output. Okay. You give me the symbol one. That is the digital. Okay, DMR. Can you give me the digital signal first? Input.
Wait lah, sir.
Hey, faster lah, mega.
Can I give you analog?
Okay, you want to give me analog first? Also can come.
Playing piano. The input
Playing
is
piano.
finger press. The output is the piano sound.
Can give digital referee.
Hey, wait.
I give digital.
Piano is analog or digital?
Yeah, should be
Digital
The
input,
input
analog output. Digital input, analog output.
No. Wait first. Piano, the key, is it on or off? How I want you to have a very definite define. You know, if you say I press the C code, D code, or E code, or F code, that one I press is a digital. Okay. If I say how hard you press, then it will be analog because I can press very slowly, softly, or hard because I'm not a musician. Then they know how to even they press on the same C code. They can give you different sound, different. I mean the wave. I don't know. Is it possible?
Yes, it's possible.
Yes.
So you need to define clearly. You know. That's why I say you need to define clearly. If you just want to say press C code or D code, that one is digital. Okay. If you press with the length or the wave of the C code or D code, that could be analog. Okay. How about output? Digital output and digital analog. Digital output analog. How about the output, guys? Come on.
Light.
Light. Okay. Why you say light?
Because there's either light or there's no light.
That one is digital input, what? Output, already there, what? No,
now
no.
we analog.
No, you want to give me like, okay lah, I accept you lah, because I put it lamb there already, ma. You cannot copy my answer. Okay. Other than like.
I didn't copy it. I didn't look at the slide. Sorry.
Okay. Other than that, actually, light also could be analog, especially for guys. You love it very much. Why the light can be analog? The output. Why?
Change color and brightness.
Brightness.
Yes, especially when you go to the KTV, karaoke, with girls. Okay. What you want to do with your room light? You want to make it very bright, or you will
Dim.
RGB.
you will dim it. Yes, you will dim it, right? When you dim the light intensity will be different. Then that one will be the analog. Can you get me? If you say open, turn on,
yes.
or turn on or turn off, it's digital. If I dim the light, then that one will be analog, because the light intensity is depend how bright or how dark, how dim you like. Okay. So
Understood.
okay, so we should move on. So as you know, why this analog and digital signal is important? Okay, before we go into this, maybe we just say actually, for the analog and digital, they can convert. Okay, if I have a analog signal, I use a analog digital converter or analog digital converter card. Okay, I can convert my signal to the digital form like this one. Okay, I will get every point of it, and then I will mark it. After that, I will generate my digital form of signal. Okay, and also if I have a digital form of signal like this one, I can convert back to the digital analog converter. Okay, where I will convert my digital signal to analog signal by adding a filter here. So I will smooth it out like this form. Okay, why we need this? Let me explain. Okay, so just now I explained to you, right? There is a ADC and DAC, analog to digital converter and digital to analog converter. So why we need this converter cards? Okay, because this one is used to convert the signal from one type of signal to change to other type of signal. For example, like ADC to DAC or DAC to vice versa. Why we need that? Because as you know, okay, our controller is what base? Can anyone tell me? Our CPU, controller, computer, all is in what base? Analog form or digital form?
Digital form.
Digital form, okay? Because how we do the computation, actually we use a digital 0 and 1, okay? And then we use a binary code, okay? 2 power of blah, then we can get a lot of number. But no matter how, they're still in a digital form. Okay, so computer in digital form. So what happened is motor. Okay, if I have a motor, this is correction unit. Correction unit will be the switch of the motor, for example. Then how am I going to control the speed of the motor? Then if I have a digital form, they cannot communicate. Okay, they cannot communicate each other. That's why we need a bridge. Where is our digital to analog converter? Okay, this one, they will have to convert the signal as like this. If I have a signal, I will convert this signal to this one. Okay, so that my motor can perform the velocity, different velocity. Okay, and for example, this is a rotating shaft. Okay, after that, then we use a deco generator. Then the takeoff generator will measure our rotating shaft. When we do the measurement, and this is what, okay, analog output. Okay, so if motor velocity is an analog output, then what will happen? The controller cannot read. They don't understand. Okay, that's why we need another converter called analog to digital converter, ADC, in order to convert into this form. Okay, when you convert to this form, then this will give a definite figure to the CPU for processing. Okay, you guys get me? Why we want analog and digital converter? In the chapter 2, 3, 4. In the chapter 4, okay. This one will be discussed in the chapter 4. I haven't uploaded the notes yet, but definitely this one will discuss further. Okay, in the form of converter. This one we did already. So the next one we want to look into it is the sequential controller. Okay, sequence. As I say, when we do the control, we have 3 types of control. The first is we want to control the value. The second is we want to control the sequence. Okay, which one happen? This one is the value. The second is the sequence. Happen B. After B, then C and D. And the third one will be the event or not. For example, like safety lock. Okay, this is a 3 types controller, which is sequential controller. Okay, in a sequential control system, a series of different events could be take place one after the others. Okay, so this is used when the control instructions are strictly ordered in a time-based or event-based. Okay, time-based means when we delay for 5 seconds. After we delay for 5 seconds, then next what you want to do. Okay, or event-based is when you sense for example, the water level. Okay, you use a level sensor. When target, then you can do the next thing. Maybe the next sequence you need to do is turn off the valve so that no more water to flow in. Okay, this is one is the time-based and one is the event-based. Both also can use for the sequential control. So the finish of one event in the sequence provide the signal for the next event to start. Okay. Conventionally, this control is by the hard wires, relays, or cam switch. Okay, so during when the PLC is not invented, I mean maybe during the 1960s. Okay, when we want to control the wires to perform the latching or circuit, all we do it is in the relay form. We use a relay to do the hard wiring control. Okay. Just like what you have looked on the experiment that you did before, relay latching. Okay. So, but however, for the modern usage, since we have a microprocessor, and this microprocessor is so powerful that it can replace all the wires type. Okay. For example, like counter or the timer. Okay. Now, inside the microprocessor, actually they have 2 functions, counter and the timer. We no need to have a physical component to do the recording because this is replaced by the microprocessor. Okay. So this is one example of the sequential controller. So for example, like we have a washing machines. Okay. So what we want to do? We have a stage like pre-wash, min-wash, rise, and the high-speed spin. Okay, for example, like the clock. So what is the clock means? That means how long you want to wash for your for your machines. So you need to let the control unit know. Okay, for example, maybe I want to use for 50 minutes wash. Okay, then this is your input. So you put it in, then the controller will do the functions. Okay, the second is the program can come in, or maybe you want to have a sport wash or normal wash or woolen fabric wash or whatever wash. There are a lot of different type of wash. I mean, in the washing machine. So you can do your select either one. Okay, you can give the input and then let the control unit. This control unit could be a microprocessor or PLC. No, normally it will not be a PLC. It's a microprocessor. Okay, so the microprocessor, the action, what they do is they will control the pump, the valve. For example, like how to turn on the let the water in or let the softener in. Heater, maybe your washing, you need preheat your water, and then the motor is the speed of your spin. Okay, and all this process, all this actuator will control your process. What is your process? Your process will be your drum will be turned. Okay, will be spin. And then what are your drum output? The output will be your water level. Okay, half full, quarter, or full. Okay, then water temperature, speed, whether your door closed or not closed. If your door not closed, do you think that your spindle, I mean your drum will spin? No, definitely no, because this is too dangerous. Okay, so all this will be get the signal from where? From the process there, from the drum there. They will send it back to the control unit. And this control unit, all this one is which one is the analog, which one is the digital? Can you tell me? Water level, is it a digital signal or analog signal? Guys?
Analog.
Analog, yes, because the water level could be half, full, quarter to half, or whatever. Okay. Temperature?
Analog.
Okay. Drum speed?
Same.
Door close?
Digital.
Digital. Okay. So this is a very basic, basic component for your washing machine automation system. Okay. So in this subject, we only consider the input and output to control the process. Okay, we don't. You guys don't learn it here. The ladder logic here. Okay. So for this control unit, okay, if in the industry, we will say PLC, programmable logic control. Okay. So in many example systems, there might be just an embedded microcontroller that being processor with memory integrated on the chip, okay, which has been specifically programmed for the task concerned. Okay, this is an embedded system. That means the program that we do cannot change. Okay, this will do according to the inventor only. So a more acceptable form of is the programmable logic control, PLC. Okay, PLC also is a micro-based controller which programmable memory to store the instruction. The instruction here will be your program. Okay, and to implement the functions such as logic, sequence, timing, counting, and arithmetic calculations. Okay, to control the event that can be ready. Reprogram for different tasks. For example, we need, this is the controller, then we need the input. Our input is our sensor. Okay, our sensor will give the information either analog or digital to the controller. If analog signal, then we need a if an analog signal, then we need a analog digital converter card before we can direct connect to the controller. If you direct connect to the controller will not understand. They cannot perform. Okay. So also for the output we have two forms. One is the digital form and one is the analog form. If digital form could be fine. Okay. This one is very direct because both is talking in the binary. If the analog, then you need a digital analog converter card to convert your signal. Okay, for example, like the motor speed, then you need a DAC. This DAC could be a variable frequency drive. Okay, I will teach you later on in the chapter 9. Okay, so the PLC actually is very well known in the automation, in the industrial automations. So this one is a continuous controller or process controller in a chemical. For example, they can work in the chemical plant, water treatment, palm oil, power, gas. If you work in the discrete controller or sequential controller, then will be the machineries, for example, like the packaging machine, material handling, pick and place applications, plastic extruder, injection machines, and all. Okay. So for you to write a PLC program, then they offer a few choices. For example, you can use a ladder logic. Okay, this ladder logic is very similar to our wiring diagram. Okay. Then it could be the NCC structural test block diagram, and also a sequential function chart. I mean, this sequence FSC is more or less like a block diagram. So for the brand, right, in the market, they have a lot. For example, like AB, Allen Bradley Logic, and this is invented by the Rockwell Automation. This is from American. Is one of the market leader. And then we have a Siemens brand from German. That is a S7 series PLC. From Japan, we have a Mitsubishi. Omron also from Japan. Panasonic. So others like Fujitsu, Hitachi, Yakawa, FATEC, Konyo, Delta. A lot of brands, they have their own controller. So even though the way that writing the controller language is different, but the concept of writing is not much different. For example, just like you write a C++ programming and you write a Java program. Okay, the way that writing will be different, but the concept, for example, they have a for loop, they have library file, all will be more or less the same. Okay, they can do the same job, but they will have a different of writing code. Okay, because they want to protect their IP. Okay, so I think you guys still very blur on the PLC, right? So I think better that I share with you guys with a video. Okay. Bear for me for a while. Just now I search it. Let's see. Okay, maybe we can have a quick look on the PLC.
There's no need to limit it to only digital input.
Sorry. Can you hear the sound, right?
Before we get into today's video, if you love our videos, be sure to click the like button below. And make sure it's of new Real Parts videos. This way, you never miss another one. The Programmable Logic Controller, or PLC, is a special purpose computer. It has no display, no keyboard, no printer, no hard drive, and hides in the control panel out on the factory floor. But it is still a computer. Initially, the PLC was a replacement for panels of relays, devices that turn on and off. Making a machine run using relays as logic was time-consuming and challenging, and making a change in the logic or the operation of the machine was almost as complicated as starting over. Relays also fail far more frequently than computer components, so that relay logic required more downtime to keep it running than newer PLC-based controls. On top of all of that, relays use a lot of electricity, make lots of heat and soot, and take up lots of space. An installed PLC is deceptively simple in appearance. You have a CPU module and input-output devices referred to as I/O. Sometimes the I/O is part of the CPU, and sometimes it is in other modules. The CPU communicates with the I/O. So in most systems, they share a backplane that physically holds them in place and electronically connects away from the CPU and connected with data cables, so that the PLC is not limited to a single cabinet or even the same building. Since the PLC is a computer, there is no need to limit it to only digital inputs and outputs. Over the years, the manufacturers added analog and other numerical inputs and outputs. To make these numerical devices useful, they included calculation capability in the programming as well, so that we can now calculate, for instance, statistical process control, or SPC values, and put PID controllers directly into the PLC program. Since this is called a programmable logic controller, we need to program it. Most PLCs are programmed using an application running on a standard desktop or laptop PLC. They communicate with the PLC using Ethernet or proprietary communication bus, depending on the manufacturer. Most manufacturers seem to have settled on Ethernet and/or USB in recent years. Unfortunately, the PLC manufacturers have failed to agree on how we program the control logic. Although most of the manufacturers claim some form of ladder logic, the specifics of that language are different for each manufacturer, including different capabilities, different ways of doing the same thing, and even differences in the order in which the CPU processes the various pieces of logic. One attempt to bring some order and interoperability to this chaos is the IEC 61131 standard from the American National Standards Institute, or ANSI. The excerpt from the ANSI webpage shown here gives a flavor of what is there. The IEC 61131 standard defines several programming languages with different strengths and weaknesses. Local programming standards, your boss or the customer, will usually specify what language you use. That wraps up this short discussion of the structure of PLCs. I hope you enjoyed this little introduction to the underlying architecture of many industrial control systems. Keep watching as we continue our exploration of the basics of industrial controls. Make sure that you head over to Real to talk about the base of
Chapter 1 that we are unable to finish on the last week. Okay, and this is the last slide.
So you're not sharing screen?
Yeah, now I'm sharing. Sorry, I
Oh,
hope
okay,
people
okay. It's
a
okay.
bit okay. So the challenge 3, so actually basically this is what I mean here. I mean what the if I want to apply this PLC in the industry for the continuous or process and also discrete control. And then as I say, there are language just now that you saw in the video, that one we call ladder logic. Okay, don't worry, when you come to the second chapter, is it DMG? Do you learn the controller?
No.
This you do not. You guys do not learn the controller. I mean,
No.
next semester.
Next semester we don't have.
Then this one will be a miss. Okay, so you will learn this one in the controller. So for DMR, you definitely learn this. Okay, then you will see the ladder logic and all this. So as I say, there are different company. So they tends to have their own way of writing the ladder logic, but the way of writing maybe is different, but the application will be the same, more or less the same, because they want to protect their IP. Okay, IP, the intellectual property, because for example, like they cannot have a same identical, else the Mitsubishi will sue the Siemens. The Siemens will need to pay the money to Mitsubishi. So that's why they come up with a different way of writing. And then after that, as I mentioned just now, the IEC, they come up with the standard. Okay, all this. So now I think we go to this one. Okay, in a closed orbit system, we what? Decrease, increase, unaffected, or any above. If you have positive gain means is your measured, your reference value bigger than your measured value. Then what will you do with your control of your correction unit? What you do? Are you going to increase the, for example, like if I want to have my motor rotating speed at 10 revolution per minute, what I found, my reference value is 10. What I found is my measured value is 9 revolution per minute. So 10 minus 9 is 1. Okay? If 1. Then what will you do with your system? Will you increase or decrease?
Increase.
Increase, okay? You will increase the speed. Okay? If negative,
Decrease.
okay. Why I can say this? Because we can look back to the error signal. Error. Here. Reference value minus the measured value. Okay? If this one reference is 10, your measure is 9. So 10 minus 9 is positive. Error signal is positive gain. So you need to increase the speed. Okay? So next, what system have tendency to oscillate? Open loop system, closed loop system, both or neither?
Closed loop system.
Okay, why the closed loop system will oscillate?
Because it gives feedback.
Yes, because it gives feedback. Because it's the error signal. Because sometimes your feedback is overshoot or undershoot. That's why you need to all the while need to control the signal. For example, like if I want to have a revolution per 10, what happens if I control to 9? Okay, sorry, I rearrange my words first. Okay, if I want my setting value is 10 revolution per minute. Okay, so after I measure is 9, so I am the gain is positive, so I need to increase. So when I increase, there will be the tendency that I will overshoot the 10. Maybe my overshoot will be 11. The measure value will be, not to say 11, 10.5. Okay, overshoot is 10.5. Then what is the next step? 10 minus 10.5 will be 0.5. Then 0.5 will be the negative gain. Then negative gain, I need to reduce, decrease. When I decrease, then there will be there will be the undershoot. So undershoot, maybe when I decrease, they will give you 9.8. Okay, because of this one, you will find out you will find out this is your 10 revolution per minute, for example, the motor speed. You will find out they will overshoot, undershoot, overshoot, undershoot, overshoot, undershoot. At the end, the differences will getting smaller and smaller and become a straight line. This could be a good control system, okay? Because at the end, you're able to control at your desired speed at 10 revolution per minute. This is a good one, okay? There also could be possible that your system is very bad. Your system is very bad that they have a tendency like this. And even greater. That means if in this case, this one we can say is out of control. Your control system can throw it into the wrong samba. Okay, that could be a possible way of this one. Okay. So feedback control system must be a function of what? Guys, a function of reference and output, input and feedback signal, reference and input, output and feedback signal. Which one more appropriate?
Output and feedback.
Output and feedback. Your feedback control system more.
Reference and output.
Huh? Reference and output.
Yeah.
What is the difference between output and the feedback signal? Okay. We eliminate first. The first one is okay. This one should be out, definitely out, because both on the same side. Like this one, reference value and input is here. Okay, actually what you want is your input here and your measure value feedback signal here. Actually what you want actually is this one. But this signal, this one is very tricky. They give you a lot of things is very similar. So which one will be the best answer? So reference and the input basically will be the same side. Output and the feedback signal also will be the same side. This is after output. Reference will be better, A or C.
A.
How many of you say A? Or anyone of you put C?
C.
C. Okay.
C.
So you and also zero initial condition for a system means what? Input reference signal is zero, no initial movement or moving part, or zero store energy, or system is rest and no energy is stored in any of this component. Okay, you give me a rough guess. Okay. All this, give me the answer next week. Okay. That's all for the chapter 1. So we move to the chapter 2 first. Okay, so the chapter 2, you guys need to focus, okay, on what? The first of all, and able to describe the performance measure, okay, of the sensor. So also need to know, evaluate the measurements of the difference between the displacement, position, proximity, velocity, motion. All this is we use sensor to do the tracking. Okay, there are a selection of sensor criteria. That means when you want to use the sensor, you need to justify. Okay, why I will use this sensor in these circumstances and use that sensor in that circumstances. Okay. So how good automation system actually is depend on the engineers or the inventor, how they're going to use the sensor, okay, to detect the environment very sensitively. Okay, it's not too, sometimes it's too sensitive, it's not good. Sometimes because it's too sensitive, they will give you a loss of false signal. If you're not sensitive at all, then you need to have your selection criteria. You know how to apply the sensor, okay? So next, as usual, we have a very generic definition. The term of sensors is used for an element which produce a signal relating to the quantity being measured. That means they want to produce a signal or to measure the quantity. Okay, for example, like the light intensity. The light intensity can be very low, very dim, and it can be very bright. Okay, this is the way we use the sensor to detect. So we have a light intensity sensor. Okay, so we also have a, for example, like we have a electrical resistance temperature element, for example, thermistor. In order to measure temperature, we have a lot of sensors, okay? After that, you will know thermistor, thermocouple, mercury type, all this, okay? And this quantity being measured is the temperature, and the sensor will transform the input of the temperature into the change resistance. For example, like this is a physical phenomenon, okay? It's a, look what they sense. They are sensed in the way of temperature, okay? And this sensing, after that, they will do the signal conditioning, which you will learn in the chapter 2, okay? Either we will need to enlarge the signal, amplify the signal, or we no need to do, or we need to protect, or we need to use a diode or whatever to make the signal. That's why we need to do some signal conditioning. That is chapter 3. And then we do the sampling. After that, you need to decide whether you need to do the conversion or not. For example, like analog or digital conversions. Then only you can interface with the computer. Okay, computer interface. This one could be the wires, all the port, and then after that, finally you will go inside to the PLC here. The PLC will be the last. So before you sense the environment changes, send to the PLC, actually you go a lot of stages. Okay, all from here will be covered in the chapter 3 and 4. Now we only consider here only. Okay, before we further on, we only consider the sensor. This one will be covered in chapter 2 or 3. 3 and 4. Then only reach your PLC or your microprocessor. So the next term you need to know is the transducer. Transducers are defined as an element that, when subject to some physical change, experience a related change to convert or to transduce the signal or energy in one form to another form of the device output. Okay, so for example, like the conversion can be from electrical to electromechanical or electromagnetics. So the transducer can be categorized in the sensor or application. That means if we're talking about the transducer, sometimes the transducer acts as a sensor, but they need to do something. Okay, for example, like we have an ultrasonic sensor. Okay, we use a sound wave to detect the speed trap of the car. Okay, for example, like the speed trap about the police, they will use the ultrasonic sensor just like a gun. Okay, they will emit the sound, ultrasonic sound, to reach the car to check the speed of the car. Okay, when the sound bounce back, then actually they can calculate with the distance and the time, then will know your speed. Okay, of the car. This is how we have the speed trap. Okay, on the highway. Okay, but if you consider just emit the sound and then receive the sound and then do the calculation, all this we call a transducer, because they involve more than one function. Okay. So, for example, like a sensor is used to detect a parameter in one form and report in another form, usually an electrical or digital signal. For example, like we have pressure sensor might detect pressure. This is a mechanical form of energy and convert it into the electricity for display at a pressure gauge. Okay, or convert it into for the PLC. Okay, then the combination of transducer will have both functions. They both detect and correct action. For example, like just now I mentioned the ultrasonic transducer, they will switch back and forth many times a second between acting as an actuator to produce ultrasonic wave and also acting as a sensor to detect the ultrasonic wave. Okay, this one will be the transducer. So, any question about the sensor, guys? Hello?
No.
Okay, if no, then we will go for the performance terminology. Okay, before we want to use the sensor, there are, I think, more or less 10 terminology you need to memorize. Not to say memorize, understand. Okay, so what are the terminology? For example, like the range, okay, or the span, okay? The range of the transducer defines the limit which the input can vary. The span is the maximum value of the input minus the minimum value. Okay. For example, a root cell or also called a weighting sensor. Okay. For measurements of force might have a range of 0 to 500 kilonewton. If I want to look at the range. So when you want to use the sensor, you need to read their specifications. For example, like this root cell can use from 0 to 15 kilonewton. That means if you want to perform your job, it's out of maybe your job is 60 kilonewton. Okay, you need to check the specimen is 60 kilonewton. Okay, do you think that this sensor can use if their specification only up to 50? Do you think that you can use this sensor? Guys, if you no, definitely no, because you are out of the range, because they will give you error reading. Okay, so you need to understand what it means by the range. Okay, and also the span. The span also is for the maximum minus the minimum value. Okay, if this value not 0, or maybe other sensor, if for example like temperature, okay, the span will be maybe from negative 10 degree to positive 10 degree. So the span is how much? What is the span?
Sir, can you repeat the question?
Okay, if I want to measure a thermometer with the span is negative 10 to 10 degrees Celsius, okay? Negative 10 degrees Celsius to positive 10 degrees Celsius, okay? What is the span for the thermometer?
20 degrees Celsius.
Okay, 20, okay? Very simple. So you need to know about the error, okay? The error is the difference between the result of the measure and the true value of the quantity being measured. That means this error is a little bit different from the error signal, okay? This error is referring to your sensor accuracy. Sometimes your sensor have problem, okay? There will be plus or minus. That cannot give you the exact figure. That's why they will tend to generate the error, okay? This is the true value, but this is the measure value. For example, like body temperature. So what I get is I just place under my knee or wherever, then I measure. Then because of maybe the sensitivity of the thermometer is not that sensitive, then maybe they will give you some error. That means the true value by body maybe is 37 degree, okay? But what I measure that I can get will be 36.9, okay? That means there will be the error of 0.1 degree. You understand? This is what I mean by the error. So, for example, if we measure a system like 25 degree, when the actual temperature is 24, then the error will be positive 1. If the actual temperature is being measured is 26, then there will be a negative value, okay, of 1. So the next term will be the accuracy. The ability of measurements to match the actual value of the quantity being measured. For example, the accuracy is often expressed as the percentage of the full range output. Okay, for example, like a sensor have an accuracy of 5 plus or minus 5% of the full range. So when we have the full range, say 0 to 200 degree, then the accuracy will be plus or minus 10 degree. Can you get me? For this one, plus or minus 10 degree, the accuracy 5%. Okay. Then the number 4 is the sensitivity. Okay, this is different. The sensitivity is the relationship indicating how much output you get per unit input. So that means it's output over input. The formula very simple. Okay, a resistance of thermometer might have a sensitivity of 0.5 ohm per degree. This is your sensitivity. How sensitive is your system? This is another error that we call hysteresis error. So hysteresis error, they might have two types, a few types. Okay, like this one. I just temporarily off the point. Okay, like a few times. Okay, so what happened is, even we get 2 points. This is the point that we want, and this is the measure. So when we do the measurement, there could be the curve here will be the different. So this will be demonstrate the increasing error. This will demonstrate decreasing error. So the hysteresis error will be the transducer can give different outputs from the same value of quantity being measured according to whether what value have been reached by the continuously increasing change or continuously decreasing change. This is called hysteresis. That means if we want to have 2 points, right, these two values, by right, you should have a linear, okay, linear line here. But in the reality, what you get, you could have the curve like this or curve like this. So this is especially when you do the experiment, right? When you do the experiment, when you plot the graph, you cannot get a very perfect line, okay, straight line to across all the points, okay? So when this thing occurs, then they will call error here. This error, if you have a decreasing or increasing of these two, we call the error of hysteresis. So we also have a non-linearity error. So for many transducers, a linear relationship between the input and the output is assumed over the working range, okay? So for example, like we have a variant method of used for the numerical expression of. So sometimes when you want to plot the graph, right, after you do the experiment, for example, like torsion or whatever, you have a lot of points, okay? So how are you going to connect the point? If you connect the point like this, okay, then actual one will be like this. Then this error. This error is due to you are assuming that your line is linear line. But in fact, the error that you have is not a linear. It's a hysteresis or decreasing area. This is a decreasing, okay? Increasing is like this. This is a decreasing, and this is increasing, okay? So when you have this one, you have a non-linearity area that you happen. Okay, if you just use two range n, you pick this point and pick this point and you draw a graph, you don't care what happened. So you also could be, if I have this type of thing, then what I try to do is I do the best fit. I think normally we apply this one. We try to do what? The best straight line for all value. I mean the least square. What you do is you try to balance out the number of point here and the number of point here. Okay, so you will draw the middle line. So when you draw the middle line, the black streak for all value, and this is the error that you happen in the reality. Okay, and the black streak line to 0 point. Okay, or you want to start from 0, because some of the experiment you definitely know if when you are 0, everything is 0. Okay, you must start on 0 and then you try to balance up. but you must fix one point as 0. This one is you're not fixing your point at 0. This one is you fitting your point at 0. And this one, I don't care. I just get both endpoint I get. So which error will be bigger? Okay. So number 7 will be your repeatability or reproducibility. Okay. So this is what is the formula for it? It's the maximum minus the minimum value divided by the full range. Okay. Multiplied by 100. This one is very important. Okay. Especially for the robotic arm. A lot of time when we purchase a robotic arm, we'll look at this repeatability. You know why? Because when we do the spot welding for robotic arm, okay, for car door, what they do is they want to do the job repeatability for the whole day. If your repeatability is low, I mean your error is too big, then the tendency of you spot the weld will be offline. That's why we need to have for robotic arm, we need to have a very high accuracy of repeatability, okay, to test the sensor whether they can keep on repeat and doing the same job or not, okay. And then you also need to know about the stability. For example, the stability of a transducer is the ability to give the same output when used to measure a constant input. So the term drift is often used to describe the change in output that occur over time. So maybe if your sensor that have the stability is not there, they will drift away your value. So when you know the value will drift away, then you need to offset it back after a certain time. Okay, you need to reset. So all this terminology actually is very important. When you really go for the industry, you need to look at the spec. Okay, you need to carefully, okay, read the spec and then whether your application environment is within your sensor range or not. If no, you better change. Okay, then there is a deadband. I mean, this is the time. The deadband of a dead space of the transducer is the range of the input value for which there is no output. That means they need a certain setup time. Okay, the dead time is the length of the time from the application of an input until the output being to respond and changes. For example, like maybe you are using a thermocouple. Maybe you need to wait for a time that the sensor cannot catch the value, then you have no meaning. That means the response time. Okay, you need to check the response time. Okay, or we call the deadband or the time. Or you also, some people will also call this one is response time. Okay, whether they respond fast or not. And we also have another one. Last one will be the resolutions. Okay, the resolution is the input vary continuously over the range. And the output signal for some sensor may change in a small steps. For example, like wire wooden potentiometer is output going up in step as the potential slider move from one wire turn to the next. Okay, the resolution is the smallest change in the input value that will produce an observable change in the output. For example, like our resolution for our robotic arm may be 0.5 degree. That means every movement they can do, the minimum is 0.5 degree. Okay. So after this one, this is all the terminology. Then we will finish the first one. You need to understand all the performance terminology. This one you need to memorize by heart. You need to understand the word. There are 10 terminologies. Okay, you need to memorize by heart. What does this mean? Okay. The next we will look at the type of sensor. So we will categorize the sensor in a type of application. For example, like sometimes we will use the sensor for displacement, positioning, and proximity. Or we also want to use in the environment for the velocity or motion. When you look at the sensor, then you will find some of the sensor could be used in, for example, like displacement, or also for the pressure, or also for the fluid flow or liquid level. For example, like the ultrasonic sensor, we can use it in the displacement and also use it in the liquid level. Okay, depend on how you use. So there are three terminology you need to know before you start the sensor. The first is displacement. Displacement sensors are concerned with the measure of the amount by some object has been moved. That means how far you move from one place to another place. This is what we call displacement. And the second one will be the positions. This one is the sensor are concerned with the determination of the position of some object with reference to some reference point. That means, for example, like you start at 0 degree, how many you are turning? For example, like 90 degree. From here to here is your positions, okay? You turn 90 degree, okay? Here is a rectangle. And then the third one will be the proximity. The proximity sensor are a form of position sensor and are used to determine an object move to within some particular critical distance of the sensor. They are essential device which giving on or off output. Actually, this proximity means here, you use the sensor to detect an object, whether this object is there or no, okay? We use the proximity sensor to detect the object, reach your position or not. So, when we do the sensor selection, then what we need to consider? The size of the displacement, which means you need to consider the range, okay? How far? Linear or angular displacement, okay? Resolutions, accuracy, what type of material or object you're being measured. Then, of course, this one is the cost. This one is your boss interest, okay? We don't want to use a very high cost, very expensive sensor to do a very simple functions, okay? Because this will increase your cost of machines or whatever, okay? It's not worth it. That's why you need to bear in mind the cost, okay? You always need to use a very low cost to give you the optimum job performance, okay? And the last one is the environment. For example, like if you want to use an inductance sensor, if you your sensor is work under a very high electromagnetic high voltage wire, next to very close, then the electromagnetic parts will going to disturb your sensitivity of your sensor. That will give you the malfunctions, okay? So all this, when you want to use the sensor, you need to consider, okay? So the first sensor we're going to show you is potentiometer, okay? This one, of course, you can see one, okay? This one we use to turn on the sound, okay? When we want to have a very loud sound, then we will twist, okay? This potential, the knob here, okay? The knob here. And we also have the linear type. This linear type is look like the equalizer, okay? When you see the DJ, when they want to play the music, they will use this linear type, okay? To play with the music. This is a potentiometer. And for the potentiometer, this is the theory. Theory sometimes is a little bit complex, okay? So because you guys is a technician or engineers, actually you no need to invent to develop the equation. I definitely not to ask you how to develop prove this equation, how it coming from, okay? But my interest is you need to know how to apply the equation. For example, like this error, what is RP, what is RL, and then what is the S squared minus S squared cube, okay? You need to know how to apply the equation, will be sufficient. You don't need to prove of how this equation is being proven. You don't need to do the proven job, okay? You just need to use the applying job. So, for example, like what is VL? Of course, I will go with you, but you don't need to memorize how to prove. I won't, because I don't think you guys should memorize it, how to prove the equations. So VL is a direct proportional to a V naught if the load resistance RL is infinite, okay? So for infinite load, the effect of the load is to transform what was a linear relationship between the output of the voltage and the angle into a non-linearity relationship like this one, okay? This is your VL. And then you need to find out the relationship. After you use the resistance formulas, then we can get RL multiplied by RP divided by this one, okay? Because we take the V equal to IR, then I is equal to same, then we will get this formula, okay? Once you get this formula, then how we do? We simplify it, we get this one. And then what is more important is we want to know the error. Then the error will be the SVS minus the FVR equal to this one. And after that, you take out your RP and RL, then you get S squared minus S cubed, and this is your final formula. Okay, you just need to remember this final formula. Then we can do the question. So consider the non-linearity error with a potentiometer of resistance of 500 ohm when at a displacement of a half is maximum slide travel, which result from there being a load of resistance of 10 kilo ohm and the supply voltage is 4 watt. Okay, so what is your RP? Your RP is your potential ohm. Okay, what is the value of your potential ohm? Actually, it's 500. And then what is your load resistance? Your RL load resistance is 10,000. Then how long you displace? Okay, for this case is half